Hi guys, it's Mr. Corzine again. I wanted to go over this word problem here at the end of your notes for 7-3. So I need that to work again, 7.3. I'll do my best here to make it legible, and hopefully you'll have a better understanding of how to set up a linear system and solve for a problem like this. So the fishing barge is leaving the dock, and it is moving upstream, so it's going against the current, and it's only going 3.8 miles per hour. So it's working against the current. But then when it returns, it travels at a faster rate, at 8 miles per hour, because it's going with the current, so it's working with it. Down here at the bottom, they provide you a lot of help. When you're moving upstream against the current, the speed of the barge in still water, what the actual speed would be, you have to take away the speed of the current. It's kind of like going against the wind if you're in a plane or something, and that gives you the actual speed. Well, what I want to make sure that you guys understand, because it is a little unclear, especially if you've never done a problem like this before, both of these are actual speeds, like what's actually happening. So let's look and see if we can set up two true statements that can make two true equations. Okay, so we've got the speed of the barge in still water, which we don't know. So when it's moving upstream, we have no idea. I'm just going to say S for still water, speed in still water. And I need to take away the speed of the current, which I also don't know. And that's going to be equal to the actual speed. In this case, when it was going against the current, it was 3.8 miles per hour. Okay. Well then, when it was going back, and remember, it's going the same distance, so there are some variables here that we don't have to incorporate because they kind of cancel each other out. It's the same distance. You actually use the speed of the boat in still water, and you add to it the speed of the current, and so it makes 8 miles per hour. So if you're looking at this, you say, well, when it was going against the current, it was 3.8. When it was going with the current, it was 8. So it has to be, the speed has to be somewhere in between this 3.8 and 8 mile per hour range. It's got to be, well, I'm thinking we have to find right in the middle. If we're looking at it purely from a algebraic standpoint, well, then we're going to see if we can cancel out one of these problems. So I'm thinking, what if I stacked these on top of each other? I'm going to move this over here, make sure I don't screw it up. Oh, I got them all separated here. Let's see if I can get this. I don't think this is any faster for me. I'll go over here like this. Now I've got a situation where I've got S minus C equals 3.8, S plus C equals 8. I can simply cancel these out if I add them together, which is what we're practicing in this topic. So S plus S, that makes 2S, is equal to the sum of 3.8 and 8. So we've got 11.8. If I want to divide that by 2, change to green here, and I divide 11.8 by 2, I believe that's going to give me something like, what is that, 5.9? So what does that tell us? Well, that tells us the speed of the boat in still water is 5.9 miles per hour. But I haven't figured out the speed of the current. I have to plug that in. So I'll take this S minus C equals 3.8, and I'll use that. So when it's working against the current, it's 3.8. I now know that the boat's supposed to be going 5.9, but it's going against the current. That makes 3.8. I'm going to subtract 5.9 on both sides. I end up with a negative value here, or, well, it looks negative here. Negative C equals negative 2.1. So C equals 2.1. So the speed of the boat in still water, what it's supposed to be going is 5.9 miles per hour. But because of the current, which is going 2.1 miles per hour, that is affecting its actual speed. So there you go. That's a little bit more practice for you guys for 7.3.